course, I really had no idea the magnitude that goes into operational efficiency, or even clearly what a bottleneck or queuing model meant. It has given me a great deal of respect and gratitude for those who work seamlessly and tirelessly around the clock to ensure operations run smoothly and efficiently. The queuing was most fascinating to me because it was the driver, I believe, for the rest of the course. Each subject thereafter had some level of queuing applied, especially the Littlefield game. I want to take a moment to thank Professor Warren for a deeply rooted deep dive into this subject. Key takeaway from Graham Warren's framework is that the performance of any queuing system is driven primarily by variability in arrivals, in service times, and in how many servers share the workload. The MMK, MD1, and GGK models illustrate a full spectrum from highly idealized but mathematically convenient systems to perfectly stable and predictable systems to highly realistic but analytically difficult models. In short, more variability means more congestion, and more generality means fewer closed form solutions. Let's look at the MMK model, which is the classic multi-server queue with Poisson arrivals, exponential service times, and parallel servers. Warren treats this as the foundational model because both the arrival and service processes are memoryless, which means the state of the system can be fully described with a simple birth death Markov chain. This structure gives us closed form results for key performance measures like the probability of delay and expected waiting time. Through the Erlang C formula, these features make MMK extremely useful for planning. Consider the MD1 model, which also has Poisson arrivals but assumes a deterministic service time. This means that the service duration is exactly the same for every customer or job. Under Warren's framework, this dramatically reduces variability, and as a result, performance improves significantly compared with MM1 at the same arrival and service rates. The analysis of this model flows through the MG1 results, where the Polizek Chinchine formula simplifies due to the zero variance in service time. The MD1 Finally, the GGK model represents the opposite extreme. Here, both arrival times and service durations follow general distributions, and there are multiple servers. This is the most realistic model, and Warren emphasizes that many real systems like emergency departments, logistics networks, or airport security behave much closer to a GGK than any Markovian model. However, the trade-off is that no closed-form solution exists for GGK. Instead, analysts rely on approximations such as Kingsman's formula for waiting times, the Allen-Koneen approximation, or full simulation models. Across all three models, Warren's core message is consistent. Variability is central driver of queuing behavior. MMK shows us a mathematically tidy but highly variable system. MD1 shows how dramatically performance improves we strip away service time randomness. And GGK shows the messy but realistic world of real operations where general patterns dominate and closed form solutions disappear. So the overarching conclusion is that the choice of model depends on the balance we need between tractability, realism, and variability. MMK provides quick conservative estimates, MD1 highlights the power of standardization, and GGK best represents reality but demands more advanced tools. Understanding the spectrum allows practitioners to choose the right tools for forecasting, capacity planning, and process improvement, anchoring all decisions in a clear understanding of how variability shapes system performance. Thank you.